Hello everyone and welcome. I'm excited to kick off today's presentation. We'll be exploring a technical guide for engineers and technicians, focusing on principles, formulas, and practical applications. Specifically, we'll be diving into steel plate weight calculation. Over the next few slides, I'll walk you through the key concepts and methods to help you with your projects. Let's get started. Let's take a closer look at the theoretical calculation balancing formulaic precision with practical tolerances. When we talk about accuracy in this context, there are two main approaches we typically consider. One is based on the SI meter, which provides a standardized, scientific way to measure dimensions. The other is the shop floor millimeter-based approach, which is more practical and aligns with real-world manufacturing tolerances. Moving on to our methodology, a key factor is the industry standard density for mild steel, which is 7,850 kilograms per cubic meter. This value is essential because it ensures consistency across calculations and helps us maintain accuracy. Remember, the fundamental physics principle here is straightforward. Weight equals volume times density. This relationship is immutable and forms the core principle behind most of our calculations. In summary, these approaches and standards help us balance theoretical precision with practical application, ensuring our calculations are both accurate and feasible within real manufacturing environments. This concept ties into our overall theme of optimizing design and production processes efficiently. Now, let's take a closer look at some of the key aspects of project estimation through competitive bidding. When we talk about crane operations, it's crucial to select the right safe lifting capacity to ensure everything is secure and efficient. Logistics also plays a vital role. Careful transportation planning and understanding vehicle limits help us avoid delays and accidents. Structural design involves thorough load analysis and applying appropriate safety factors to protect both the structure and the workers. Material procurement is another critical area. Accurate costing and precise ordering help us stay within budget and avoid shortages. So, why is accuracy so vital? Because in critical applications, even small errors can lead to costly mistakes or safety risks. This slide highlights how each element feeds into the overall success and safety of our projects, reinforcing the importance of precision at every step. Let's take a closer look at some fundamental concepts. First, the standard density for mild steel is typically around 7,850 kilograms per cubic meter. This value tells us how much mass is contained in a given volume of steel. Density, in general, is all about mass per unit volume, so it helps us understand how tightly packed the material's particles are. Next, volume refers to the three-dimensional space that an object occupies. Whether it's a block of steel or any other material, volume is essentially the size of that space. Understanding these components is crucial because they're the building blocks of the basic physical laws that govern material behavior. Appreciating how density and volume relate helps us analyze and predict how materials will perform in different conditions. So, when we talk about the fundamental physics behind materials, these concepts are foundational. They help explain why materials behave the way they do under various forces and environments. Let's talk about the density of standard steel. As you can see, specialized alloys can have different densities. For example, stainless steel has a density of about 8,000 kilograms per cubic meter. But for our purposes, we use a standard value. This value acts as a constant in many simplified engineering formulas, making calculations more straightforward. Now, where does this number come from? It's based on the average density of iron, which is approximately 7,870 kilograms per cubic meter. This value is then adjusted slightly to account for the carbon content in steel. The figure we settle on, 7,850 kilograms per cubic meter, is actually the industry standard for mild and carbon steels. It's universally accepted, so when you're doing calculations or designing structures, you can rely on this consistent value. And the reason we choose 7,850 rather than the exact 7,870. It's mainly to have a rounded, practical number that simplifies calculations while still being very accurate for most engineering purposes. All right, let's break down the next steps. First, we multiply by 7,850 kg per cubic meter. This number represents the density, which is crucial for calculating mass or volume when we have the other measurement. Next, we move on to calculating the volume in cubic meters. To do that accurately, we need to make sure all our dimensions are converted to meters first. This step ensures consistency and correctness in our calculations. Finally, before jumping into calculations, it's important to do a unit check. Always verify that your measurements are in the correct units, here, meters, to avoid errors. This step-by-step approach, especially using the direct calculation and the SI unit formula, helps us stay organized and accurate. Remember, understanding these key points keeps our calculations reliable and aligned with the overall goal of precise measurement. All right, let's dive into this example. We're asked to calculate the weight of a mild steel plate, and the key dimensions are provided here. First, let's look at the thickness, which is 10 millimeters. To work with the volume formula, we need to convert that to meters, so 10 becomes 0.01 meters. Next, we have the width of the plate, which is 1 meter, and the length, which is 2 meters. So, with these dimensions, we can find the volume by multiplying length, width, and thickness. Once we have the volume, we'll multiply it by the density of mild steel to find the weight. The density is typically about 7,850 kilograms per cubic meter. So, in summary, convert all measurements to meters, calculate the volume, then multiply by the density to get the weight. It's a straightforward process once you have all the dimensions in consistent units. This example really highlights the importance of unit conversion and applying basic formulas in engineering calculations. So, one of the great advantages here is that no manual unit conversion is required, which simplifies the process quite a bit. When we see 10 to the power of -6, or 10, that's actually a handy factor for converting volume measurements from cubic millimeters to cubic meters. It's a small number, but it makes a big difference in ensuring our units are consistent. Next, we have the number 7.85. This is our density adjustment factor, derived from dividing 7,850 by 1,000. It's used to account for the material's density, especially when dealing with steel or similar materials, and it helps us convert measurements into the correct scale for calculations. Now, you might be wondering, why does this approach work so well? Well, it's because in manufacturing, measurements are often taken in millimeters, but for the calculations we need to do, working in meters makes more sense. Using these conversion factors streamlines the process and reduces the chance of errors. Finally, this is what we call the shop floor formula, specifically Formula 2, focused on millimeter units. It's designed to be straightforward, practical, and directly applicable in real-world manufacturing environments, making our calculations more efficient and reliable. Now, let's look at how we combine these key concepts. First, we start with the density adjustment, which is crucial for ensuring our calculations reflect the actual material properties. Next, we consider the simplify factor, a handy tool to make our equations more manageable without losing accuracy. When we talk about volume, remember that the basic unit conversion is 1 millimeter equals 0.001 meters. This helps us maintain consistency in our measurements. And finally, it's important to note that the formula we've derived is mathematically exact, based on fundamental principles. All these steps come together in our mathematical derivation, which provides a solid foundation for understanding the behavior we're analyzing. So, by combining these elements, we're able to develop precise and reliable models that are grounded in fundamental science. All right, let's break down what we see here on slide 10. We start with a result of 157 kilograms. This is the weight we've calculated after the initial step. Next, we move to step 2, which involves multiplying by the specific gravity or density factor to find the volume. Using the shop floor division method, specifically method B, we arrive again at that same 157 kg, so this confirms our calculation's consistency. Now, to find the volume, we multiply by the density factor, which in this case gives us a volume of 20 million cubic millimeters, or 20 million 3. Notice that we're using scientific notation here to handle such a large number efficiently. Moving on to method A, the standard approach, we look at a plate dimension example, 2000 by 1000 with a thickness of 10. This helps us visualize how the volume is calculated in a more conventional way. Finally, this slide compares two methods, Method B, the simplified shop floor approach, and Method A, the standard method, highlighting their results and how they relate. It's all about ensuring accuracy and understanding how different approaches can lead to the same outcome, which is essential for reliable manufacturing calculations. Throughout, the key takeaway is that whether you use the simplified or the standard method, you should arrive at consistent results, reinforcing the importance of understanding both approaches within our overall manufacturing process. All right, let's take a closer look at some of the key data points here. The factor we're using is 7.85 times 10 to the minus 6, which plays a crucial role in our calculations. The raw volume, measured in millimeters cubed, is 45 million. When we convert that to cubic meters, it becomes 0.045 cubic meters. Now, looking at the dimensions, the length is 2,500 millimeters, the width is 1,200 millimeters, and the thickness is 15 millimeters. To express that in meters, we have 2.5 meters by 1.2 meters by 0.015 meters. This helps us visualize the size of the plate we're working with. It's important to note that the thickness T is 0.015 meters, which is the same as 15 millimeters. We also have a millimeter solution versus a meter solution, indicating that we've verified our calculations in both measurement systems and everything checks out. Finally, the overall dimensions of the plate are 2.5 meters long, 1.2 meters wide, and 15 millimeters thick. This example illustrates the complex calculations involved in translating raw volume data into practical measurements, ensuring our consistency throughout the process. Now, let's take a closer look at this quick reference table, which summarizes how we can estimate the weight of different materials based on their input units. Starting with meters, this is the most common unit for larger structures. The formula here is length times width times thickness, multiplied by a constant factor of 7,850, which is the density in kilograms per cubic meter. So, if you're designing offices or working on projects that follow the SI system, this method is quite straightforward and accurate. Moving on to millimeters, which are used for smaller, more detailed components, especially on shop floors or in manufacturing settings. The formula remains similar, length times width times thickness, but the constant factor adjusts to 7.85 times 10 to the negative 6. This slight change accounts for the smaller units, maintaining accuracy in your weight estimations. Lastly, for centimeters, which can serve as an alternative metric for estimation, the formula again is length times width times thickness, with a constant of 7.85 times 10 to the negative 3. This makes it convenient when working with slightly larger measurements, but still within a metric context. The key takeaway here is that by adjusting the constant factor according to the input unit, you can quickly and reliably estimate weights across different measurement systems. This table serves as a handy reference to streamline your calculations, whether you're in the early design phase or doing detailed manufacturing planning. Let's start with an important tip. Always check the mill certificates before proceeding with any materials. These certificates confirm the material's specifications and quality, ensuring we're working with the right material for the job. Next, when considering weight, keep in mind that the theoretical versus actual weight typically varies by about 2 to 5%. This is quite common, especially with rolled plates, because they tend to have some thickness variations. It's important to account for these differences during planning and fabrication. Now, regarding practical tolerances, manufacturers usually specify acceptable ranges for material dimensions and properties. For example, in the table here, you can see the approximate densities for various materials. Stainless steel 304, for instance, has a density around 7,930 to 8,000 kilograms per cubic meter, while aluminum is much lighter at about 2,700 kilograms per cubic meter. Understanding these material variations and tolerances is crucial because they directly impact the weight, strength, and overall performance of your components. Always keep these factors in mind to ensure your designs are accurate and reliable. Let's talk about some common pitfalls and best practices to keep in mind. First, it's really important to document our density assumptions clearly. This helps ensure everyone is on the same page and reduces errors down the line. Next, I recommend using software templates for repetitive tasks. This not only saves time, but also minimizes manual mistakes. Always double-check all decimal point conversions. A small oversight here can lead to significant inaccuracies. Before performing calculations, make sure to standardize your units. Mixing units like meters with millimeters can cause confusion and errors, so consistency is key. Also, be cautious about rounding numbers too early in your process. Early rounding can compound errors, so it's best to keep precision until the final step. When dealing with critical lifts, don't ignore rolling tolerances. They can be crucial for safety and accuracy. Another common mistake is using the wrong material density, such as applying mild steel density for stainless steel or aluminum. Always verify the correct material properties. And finally, avoid mixing different units within the same calculation, like combining meters with millimeters, as it can lead to miscalculations. By keeping these best practices in mind, we can greatly improve the accuracy and safety of our work. Thank you so much for being here and for your attention throughout this presentation. If you found this content helpful, I would really appreciate it if you could subscribe to my channel. That way, you'll stay updated with more engineering and technical tutorials that I regularly share. And if you're looking for a ready-made steel weight calculation sheet, just leave your email ID in the comments section. I'll be happy to share it with you directly. Remember, when it comes to implementing standardized calculation templates, consistency is key. Using methods like the meter and millimeter approaches, you'll find they produce identical results, which helps ensure accuracy and reliability in your calculations. And as a quick reminder, the fundamental foundation for calculating weight is simple. Weight equals volume multiplied by density. Keeping this formula in mind keeps your calculations straightforward and correct. To summarize everything we've covered today and to prepare for the next steps, I encourage you to practice these methods regularly and adopt the templates I've shared. This will help you streamline your work and improve precision. Once again, thank you for your time and attention. I look forward to seeing you in future tutorials.